Hello, physics students. Part two of this week of the physics of superheroes, we're going to look at Spider-Man, impulse and momentum. We're reviewing some of the concepts of impulse and momentum, and we're going to call this web slinging and swinging. And we're off. This is how this looks. First thing you should know about Spider-Man is that with great power comes great responsibility. You have been endowed with great power in your knowledge of physics, and you'll just need to make sure that you use that power wisely. And so we're going to use that power wisely to solve a problem. Let me give you some background. In 1973, a series of comic books was printed. Spider-Man predates that 1973, but by 73, Spider-Man had a girlfriend named Gwen Stacy. And so two things you need to know about. First of all, that means Spider-Man must be in his 60s by now. And second is Gwen Stacy, the girlfriend of Spider-Man, died in a fall from the George Washington Bridge in a comic strip, okay, in a comic book, Spider-Man comic book. So here's how this played out. We have George Washington Bridge, Spider-Man, you can't tell from here, but there he is way up there saying, no, because it's slow motion and Gwen is falling. And then he shoots his webs off to stop her before she hits the water. He's urging his webs on to catch her, catch her, catch her, and ha-ha, did it, success, captured her and pulled her up to back up to the top of the bridge. Hooray! Except she didn't survive the fall. Actually, this is kind of a big nerdy debate among comic book people about what caused Gwen's death. Was Spider-Man's stopping her so quickly the cause of her death, or was she just did her heart stop on the way down? So believe it or not, you probably can believe this. This is a seriously debated question, along with who is stronger, the Hulk or Superman, and who is faster, Flash or Superman. Those three things you're going to incite riots at a comic book convention if you just toss those questions around lightly. So again, with great power comes great responsibility. Don't toss those questions around lightly. But we're going to see what force is necessary to stop Gwen's fall here. We're going to have to make some assumptions like we did with Superman and his mass and all that stuff, but we can do that. We're comfortable with this. So here's the big concept. We can use what we know of physics to determine the force necessary to stop Gwen Stacy's fall. Hooray! First thing we need to know is how fast was she moving when she at her fastest? And we need to take a little detour here just because as long as we're in the realm of nerdiness. In the comic book, they explicitly say that it was the George Washington Bridge that she fell off, but people who know New York, which I don't, say that's not the George Washington Bridge, that is actually the Brooklyn Bridge, and this is a photo of the Brooklyn Bridge. And Stan Lee of Marvel Comics fame admitted and took responsibility in 2004 that, yes, that was actually the Brooklyn Bridge, and they had misnamed it incorrectly as the George Washington Bridge. So there's your nerdy little detour for the day. In all subsequent reprintings, they've corrected that to the Brooklyn Bridge. So, okay, at any rate, we're going to assume that Gwen Stacy fell 300 feet. You know that 1 foot equals 0.305 meters. If you don't know that now, you do because you're reading it and you're hearing me say it. So your first task is to calculate how far was Gwen Stacy's fall in meters. Just a reminder, there are 4 calculations you're going to need to perform today, and those are going to be those are on the assignment for this week, the superheroes assignment. So you'll need to open up that assignment and actually record those calculations there. How far was Gwen Stacy's fall in meters? Now, we need to know her maximum velocity. Fortunately, there's a kinematic equation that relates her initial velocity and the acceleration of gravity and the distance she fell to determine her final velocity. So, her initial velocity vertically was 0. She fell from rest, and then she didn't push herself downward or anything. She just fell from rest. That's the assumption. So initial velocity is 0, The acceleration of gravity is still negative 9.81 meters per second squared, and the distance she fell is what you just calculated on the previous slide. So your task here is to calculate how fast was Gwen Stacy falling in meters per second. Don't forget that when you plug these numbers in, you're calculating v sub f squared, or final velocity squared. You're going to need to take the square root of that. If you didn't do that yesterday for solving Superman's velocity question, you're going to need to remember to do that. So square root that bad boy. Now, we know how fast she is moving, but we need to know the force necessary to stop her fall. And to know that, we're going to visit the concepts of impulse and momentum. So here's the formula that you guys knew last semester. This left side of the equation is called impulse, and it's force times change in time. And the right side of the equation is momentum, delta P. P stands for momentum. So that's impulse equals the change in momentum. So that's what that equation literally means. Here's how we're going to break that down. There's our impulse momentum equation. Momentum is mass times velocity. So we're going to assume that Gwen Stacy, we need to know her mass. We've calculated her velocity. We need to know her mass in kilograms. So we're just going to assume that Gwen Stacy weighs 110 pounds, and you know that 1 kilogram equals 2.2 pounds. So calculate Gwen's mass in kilograms. I'm going to fix this right now. Gwen's mass in kilograms. There we go. Chunk, 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 chunk. There it is. Calculate Gwen's mass in kilograms. That's your next thing. Okay, done. There's our impulse and momentum formula. And we're going to break it out a little further. Change in momentum is final momentum minus initial momentum. Here's what I want you to, we're going to have to flip this on our heads. We're now talking about the time it takes Gwen Stacy to stop. So when she fell, her initial velocity was 0, and her final velocity was the maximum value. For this last part of from here on out, we're going to be calculating her deceleration, the time it took her to slow down. And so that means her final velocity is 0. Her initial velocity is the maximum velocity you calculated earlier. So change in momentum is final momentum minus initial momentum. Momentum is mass times velocity. So this becomes force times time equals Gwen Stacy's mass times her final velocity minus her mass times her initial velocity. Her final velocity is 0 because she stopped. So this becomes the equation, and we can get rid of this term, and it becomes force times time equals negative mass times initial velocity. And we're solving for force eventually. So let's divide both sides by delta t, and this becomes our equation. Force equals negative mass times initial velocity divided by change in time, divided by time. So next step, there's where we left off. There's our equation. Gwen Stacy's mass, you calculated it in kilograms. Her initial velocity, you calculated this. It's her final velocity during free fall. It's her initial velocity during slowdown. T, we're going to assume is 0.5 seconds. And this is kind of, this is just based on, I mean, this is a big assumption, but it's based on that picture that shows Spider-Man stopping her shortly before she hits the water. So we're just picking a t value based on how long it took her to go from her maximum speed to her 0 speed. And last thing, calculate what force was applied to stop Gwen's fall. Once we do that, we do what we need to do. Here's something interesting. If you compare the stopping time for bungee jumping, you see a huge difference. Those bungee cords, and this video, by the way, is here and it's live in the slideshow, and it's pretty fun to watch, so I'd recommend pulling up the slideshow and watching it. If you pay attention to like when the cord starts stretching and when the bungee jumper finally stops, they get their stopping time, their delta t, is a pretty big value. It's a few seconds long. So that force that's applied, oh no, my computer's going to die. That force that's applied to slow down this guy on his bungee jump can be a lot less. The change in momentum, the right side of that equation, doesn't change. The velocity doesn't change, the mass doesn't change unless you have some terrible accident and lose a limb. The mass doesn't change. And so the left side of the equation, the way you can modify the force is by changing the time it took to slow down. So this guy here is going to take a much longer time to slow down, so it can take a much smaller force to do it. If Spider-Man were stopping this guy in half a second, it would take a large force to do that. Okay. Go be awesome.